Okay, question 1, we're looking at a spectra of a star which is in an orbit and it's moving towards us and away from us over its orbit. When it's moving away from us, it's doing so at 400 kilometers per second on this side, and on this side of its orbit it's coming towards us at 400 kilometers per second. So the wavelength is going to be shifted. On this side it's coming towards us, so the wavelength is going to be shortened, so it's going to be blue shifted, and on this side it's moving away from us. So it's going to be redshifted. So we need to work out what the wavelength of the star is going to change to. So the wavelength of the star, we are told in the question, is lambda equals 656.28, and it's in nanometers, so it's times 10 to the minus 9 meters. Well, how fast is it moving away from us? 400 kilometers per second. So we can use our equation for the change in wavelength as a fraction of wavelength equals v over c. Okay. And this will then give us delta lambda, our change in wavelength, equals v over c multiplied by lambda. And v is 400 kilometers per second, which is 400 times 10 to the 3 meters per second, because we do everything in meters, divided by the speed of light, which is 3 times 10 to the 8 meters per second. And then we multiply this by our wavelength, so multiplied by 656.28 times 10 to the minus 9. And this gives us a change in wavelength of about 0.875 times 10 to the minus 9 meters. So that is our change in wavelength, and when it's coming towards us, the wavelength will shrink by this amount. When it's moving away from us, the wavelength will increase by this amount. So we can just do lambda max equals lambda plus delta lambda. Okay. This gives us 657.16 times 10 to the minus 9 meters, and lambda minimum equals lambda minus the change in lambda, which gives us 655.41 times 10 to the minus 9 meters. Okay, question 2. We've got a radio wave of wavelength 2.7 meters transmitted from the Earth to the Moon. Shows that the frequency falls within the radio window, which is given to us. Well, it's a photon, so we can use v equals f lambda, and v is c, the speed of light, because it's a photon. So f is therefore c divided by lambda. Speed of light is 3 times 10 to the 8 meters per second, and the wavelength is 2.7 meters. So for this we get a frequency of 1.1 times 10 to the 8 hertz. And I could also write this as 111 times 10 to the 6 hertz. And times 10 to the 6 is mega, so this is 111 megahertz, which falls inside the radio window of 30 megahertz to 300 gigahertz given in the question. So this photon is a radio wave. Part 2, this effect is called the Doppler effect. Not a redshifting or blueshifting, but the Doppler effect, because the Doppler effect covers both of them. Okay, next part. Calculate the relative velocity of the Earth and Moon when the frequency of the received signal was 300 Hz greater than the transmitted frequency. Well, as well as using delta lambda over lambda, we can also show relatively straightforwardly that this is also equivalent to delta f divided by f equals v over c. Therefore, v equals delta f over f multiplied by c. Well, we've been told in the question that the change in frequency is 300 Hz. So delta F is 300. And we worked out in the previous question that the frequency was 111 megahertz. So 111 times 10 to the 6, or 111.1. Going. Multiply them by the speed of light, which is 3 times 10 to the 8. This gives us approximately 810 meters per second, because it's a speed. Question 3. Images of the sun show change in wavelength due to the Doppler effect of one side of the sun approaching the sun, the earth, and the other side receding from the earth. So, using our equation for the Doppler shift, we've got delta lambda divided by lambda equals V over T. So for this first one, when the edge is moving away from us, the wavelength is going to increase. So delta lambda is going to equal to lambda bracket V over T. It's going to increase, so the change in wavelength will be positive. However, when the light comes from the edge that's moving towards us, the wavelength is going to decrease. So the change in wavelength is instead going to be equal to minus lambda V over C. So it will squash and stretch by the same amount. If it's moving away from us, it will increase. And if it's moving towards us, the wavelength will decrease. Okay, so the apparent wavelength of a line of original wavelength 589 nanometers is measured from photographs showing opposite ends of the diameter of the sun. And the difference between these readings is 78 times 10 to the minus 3 nanometers. So, again, delta lambda over lambda equals V over C is the equation we're going to use. But what are we going to use for the change in wavelength? Well, think of what the question has told us. We are observing the sun. Here's our eye, observing the sun. Well, the difference between the readings at opposite ends of the diameter of the sun, one end is going to be coming towards us, and one end is going to be going away from us, because the sun is rotating. So the difference between this top reading and this bottom reading is 78 times 10 to the minus 3 nanometers. But that means that the difference between the wavelength here, for example, where it's not moving towards or away from us, is going to be half of this amount. So when you rearrange this equation to get your speed, you're going to have V equals delta lambda over lambda times C. But delta lambda this time is half of the value they've given us in the question. So we'd write this like 78 times 10 to the minus 12 divided by 2. There's a divide by 2, and also the wavelength read as well, which is times 589 nanometers, or times 10 to the minus 9, and then times by the speed of light, 3 times 10 to the 8. So when we plug this in, we get about 1986 meters per second. And then for the second part, we then need to use this speed to work out what the angular speed is. Well, remembering the circular motion part of the course, omega equals V divided by R, where omega is the angular speed of rotation, V is the linear speed, and R is the radius of the circle. So V divided by R then becomes 1986 divided by the radius of the sun, which we're given as 7 times 10 to the 8. And so we get an angular speed of about 2.8 times 10 to the minus 6. And the units for angular speed are radians per second. Question 4. We've got a diagram showing two stars A and B that are forming a binary star system, so they're orbiting around each other. The two stars are orbiting the centre of mass and at about this point here in the centre, and the Earth is in the same plane, so we're looking at these binary stars. The next figure shows part of the spectrum of star A when it is in position R. So position R is here, the closest part of the orbit. And here's the spectrum that we see, this top spectrum here. So these are the coloured lines that we see when we point our spectrometer at the star. These are the emitted frequencies of light from the star that we see as lines on a spectrograph. Explaining your reasoning, draw in the boxes below the same part of the spectrum when it is at P and Q respectively. So here's P and here's Q. Now we can look at the arrows for the rotation, and so at Q it's going to be coming towards us, and at P it's going to be moving away from us. So let's look at P first of all. When it's at P, it's moving away from us. So all of the light is going to be redshifted. All the light will be redshifted at P. So in this first one we're drawing, what happens at P? If all of the light is redshifted, that means the wavelength is going to increase. So instead of being here, the wavelength will be to the right of where these lines are bit. That's if it's a P. What if it's a Q? Well, if it's a Q, it's now coming towards us. P is moving away from us. So it's now coming towards us at Q, which means that it's going to be blue shifted. So the wavelengths will actually be squashed slightly. So instead of the wavelength increasing, the wavelength will slightly decrease instead. These lines showing the decrease in wavelength. An explanation. Well, why does this happen? Well, the reason is because at different parts of the orbit, the lines are going to be squashed, so the waves are going to be squashed or stretched. At Q, it's coming towards us, so the wavelengths will decrease. At P, it's moving away from us, and so the wavelengths will increase. And so you get the stretching or the squashing of the spectrum from the star. Okay, question 5. The calcium line from a laboratory source has a wavelength 3.9342 times 10 to the minus 7 meters. The same line when measured in the spectrum of the star when it's in position S is figure 1 and has a wavelength of 4.7804 times 10 to the minus 7 meters. Calculate the velocity of the binary system. Well, let's start off with the equation. So delta lambda over lambda equals B over C. Well, we can rearrange this. So V equals delta lambda over lambda multiplied by C. Well, what is delta lambda? Well, delta lambda is this wavelength measured in the lab minus this wavelength measured in the star. So the difference in these is going to be 4.7804 times 10 to the minus 7, so minus 3.9342 times 10 to the minus 7. That's our delta lambda, divided by lambda, which is 3.9342 times 10 to the minus 7, and then multiply by this p of light 3 times 10 to the 8. So this gives us something around about 6.5 times 10 to the 7 meters per second, and it's moving away from Earth. So positive velocity means moving away from Earth because the lines have been stretched. Okay, next part, slightly trickier. We've got the same calcium line and we measured its location in the spectrum, and it varies from this wavelength to a minimum of this wavelength over a period of 120 days. We've got to work out the radius of the orbit. Well, we've initially got to try and work out the speed that it's orbiting with. We don't care about how far the cluster is, how fast the cluster is moving away from us like we have in the previous part. In the previous part we've just worked out the velocity of the system as it moves away from us. Very, very high speed. But we don't care about how far it's moving away from the Earth. Now we're cared about how fast it's moving in its own orbit. So what is the change in the wavelength that we see from the system? Well, let's look at the diagram. In position S, it is here. Position S, it is not moving relatively towards us or relatively away from us. So here we're going to get the middle value for the wavelength. When it's on position Q, it's going to be relatively coming towards us, and in position P, relatively moving away from us. So we need to look at the change in wavelength that we get when it's doing that. So the wavelength change that we get, the central wavelength, is going to be the one that's given to us in the previous part of the question, which was 4.7804 times 10 to the minus 7 meters. That's the wavelength that we use, the central wavelength. And how do we use our equation for V? Well, in the previous part, we've got V equals delta lambda over lambda multiplied by the speed of light, c. So if we plug the values in, we can work out what the change is. So in our change of wavelength, we've got 0.0132 times 10 to the minus 7 divided by the wavelength, which is 4.7804 times 10 to the minus 7, and then multiplied by the speed of light. But where does this top value come from? How does the change in wavelength? Well, it's the difference between this wavelength, 4.7804, and either of these, 4.79 and 4.7672. So this is the change in wavelength between this central value and the maximum or the minimum. So the speed that we get, we can work out as about 8.3 times 10 to the 5 meters per second. That's the orbital speed of the star. Well, we're also told in the question that the period is 120 days for it to vary. Well, if it's varying from its minimum to its maximum, it's basically doing half of the orbit. So in 120 days it does half of an orbit. So we can work out that the period for a full orbit, t, is going to be equal to 240 days. That's the time it takes to do one complete orbit. And then we can use the equation from circular motion. 2 pi r is the circumference of a circle. That's the distance it travelled. The distance divided by the time is equal to the speed. So we can rearrange this to find r. Rearrange this equation, you get r equals t v divided by 2 pi. And of course we've got to convert t from days into seconds. So we get 240 multiplied by 24 by 60 and by 60. That's converting days into seconds. And then times by our speed, which we've already worked out, 8.3 times 10 to the 5 meters per second. And then divide by 2 pi. And we get a speed of approximately 2.73 times 10 to the 12. So a radius of 2.73 times 10 to the 12 meters. That's approximately the radius of our orbit. These stars in a binary system. Question 6. What is meant by the Doppler effect? Well, the Doppler effect is an increase or a decrease in the frequency of the waves seen by an observer and an emitter moving relative to each other. and then explain how observing the spectrum of a star and applying the Doppler equation to the experimental observations enables the speed of recession of the star to be obtained. So we've already done this in the previous several examples, but we can measure a change in the wavelength. Let's start with the equation. Change in the wavelength and a fractional change in the wavelength, so delta lambda divided by lambda, is related to the speed the object is moving away. So we can listen for the stretching of the wavelength and use that to estimate v by doing v equals delta lambda divided by lambda multiplied by c. And how do we get lambda? Well, we can measure lambda, the base frequency, in a lab, for example, and we get the raw value, and then we can measure the equivalent lambda observed from the star with a telescope or spectrometer or similar.